Okay, let's continue. So, I explained, we can express, rewrite this as, this, because if you take, the cross product of these two vectors, you will get it in this result, Now see, this one is geomagnetic field, Bxi, this is the x component of field, this is y component of field, this is, z component here. So your magnetic field has been expressed in component forms there, rectangular components. And here, what about IAB represent? See here, you have current. A is one side of your rectangle, B is another side of your rectangle. It means, this AB, this AB represents area of rectangle. This represents an area of a rectangle. So you have a current times area, and started, this represents current times area. If you have only one turn of loop, then this represents magnetic moment. This represents magnetic moment, magnitude of magnetic moment. And here in a K, K vector, unity vector K represents direction of magnetic moment. So this IABK is representing magnetic moment of your current carrying loop, and B is the uniform magnetic field in which your loop is located. So this might be clear. And is it clear now? Now let's move to another slide and see. Okay, fine. And in this case, we derived this formula using a rectangular loop. But you can apply this formula for current carrying on a loop of any shape, whether it is circular, if you're in a loop, current carrying loop is circular, then your magnetic moment will be how much? Magnitude of magnetic moment, it will be IA and I pi r square. If r is the radius, if you have one turn, then IA. If you have n turns, then NIA. So you can apply this formula for any current carrying loop placed in a uniform magnetic field. And see here, our torque is a cross product of magnetic moment and magnetic field. So what will be the magnitude of this cross product? This is simply magnitude of first factor and magnitude of second factor into sine of angle between them. Here theta is the angle between magnetic moment and the magnetic field. See, what will be the direction of magnetic moment of this loop? Yesterday, we discussed. What will be the direction of magnetic moment of this loop? Tell me fast. Your loop has anti-clockwise current. Just close this one. Okay. How do we find the direction of the magnetic moment? We call the fingers of right hand, the four fingers except a thumb in the direction of current. Then your thumb points in the direction of magnetic moment. So your magnetic moment here is what? Your inward. Magnetic moment is inward. Okay. So you can apply this formula for any current carrying loop placed in a uniform magnetic field. So now if the angle is 0 degree or 180 degree, then what will be the torque? Your sin 0 is 0, sin 180 is 0, and torque is 0 degree. Torque will be 0. Similarly, if your angle is 90 degree, then torque is maximum. And see, here we have written the magnitude of our torque. It is magnitude of your magnetic moment is NIA, and NIA represents magnetic moment, magnitude of magnetic moment. NIA and be the magnetic field. If you have only one tone, and then you will have a current times area. This is how we calculate torque due to any current carrying a loop in a uniform magnetic field. So now let's discuss a few general things. Let's move to the next slide. We need a blank slide now. To here we add in a PowerPoint. No. Okay. Now let's correlate our concepts with electrostat. Let's draw in the first we write you might have studied an electric dipole. Here we have a magnetic we can call current carrying loop a magnetic dipole because it has a magnetic field, it has a north pole and a south pole. We already discussed in yesterday. So what is the similarity? In electrostat, you might have studied electric dipole means minus Q, a pair of equal charge, a charge of equal magnitude and opposite nature placed at some distance apart. Say, if you're in a distance, here is, if your distance here is L or D, then you can write in a dipole in a moment as charge, magnitude of charge times, this is a distance of separation. So, electric dipole, here we'll have an electric dipole, and dipole moment, magnitude of dipole moment is represented by P, and it will be charge, magnitude of charge times length. In some book you might have seen formula as Q into 2L or 2D. If the separation is, if you take the separation as 2D, then the formula will be Q into, let's take D. We are taking the separation as it is, so it will be charge times separation, distance of separation. And what is the direction of dipole moment? Direction, it is from negative charge to, or you can simply write minus Q2 plus Q, minus Q2 plus Q. Dipole moment, first and here magnetic moment, and magnitude of magnetic moment. This is a magnetic moment, and it is NIA, where N is the number of turns, I is the current in the loop, and A is the area. Now, what about net force? Net force in uniform field. In uniform field, if you place an electric dipole in a uniform electric field, you might have found out the force. Here also 0 and here also 0. We already studied this in 0. We are just studying similarities there. What is the similarity? You have studied this in electrostat. Now, what about the torque? Torque in electrostat, we write in a torque as electric dipole moment times electric field intensity. Here what we write? Here we write in a torque equal to, we studied we write M cross B. Now potential energy, though we don't have to study this now, it has been removed from the syllabus. So I think I checked out the syllabus coordinate. It is not there, but you might have found out in the book that you in electrostat you have U equal to your energy, potential energy is a scalar quantity, and U is negative of the dot product of your dipole moment. And here also we have we can write in a similar manner negative of M dot B. Dot product is a scalar quantity. Your potential energy is a scalar quantity. Now work done in a rotating in a dipole. This one is let the rotation be from θ1 angle to θ2 angle. Then we write it as PE cos θ1 minus cos θ2. You can write initial potential energy minus PE cos θ1. No, the value of dot product is how much? PE cos theta. No, and in initial position you have this potential energy, and at final position you have minus PE cos θ2. So the work done will be how much? Negative of change in potential energy. Work done by a conservative force, and work done by a conservative force is negative of change in potential energy. So you can write U2 minus U1, and you can put the values and get this result. You might have studied this in mechanics. Work done by a conservative force is negative of change in potential energy, and our electric force is also a conservative force. Okay, and in similar way, here we can write work done in a rotating magnetic dipole or loop from θ1 to θ2 angle. It will be MB cos θ1 minus cos θ2. Cos θ2. Let's save this one because we don't have PowerPoint now. This is just a similarity. You might have studied all these things in electrostat, and I am correlating with the magnetism. But in current syllabus, these formulas, these derivations have been removed if you check the latest syllabus of NEET. So we save this one, I think. Now let's clear this one, and Electric field. Next quantity, again here we have electric dipole, and here we have a magnetic dipole or a current carrying loop in a uniform magnetic field. Now let's find field along axis. Field along axis means this is your minus q, this is your plus q, and your point lies along the axis means along the line joining the 2-point charges, and you have to find the net field at this point. So this formula here is 1 by 4 pi epsilon naught 2p by r cube. If you write in vector form, then you can put here where p is dipole moment, where p is dipole moment. And in a similar way, here also we have magnetic field at a point, due to a magnetic dipole or a current carrying loop in a uniform magnetic field as mu naught by 4 pi. Here you wrote electric dipole moment. Here we will write magnetic dipole moment by r cube. And if you write in a vector form, then see, except magnetic moment, all quantities are scalar. This is 4 pi. Let me edit. This is 4 pi mu naught by 4 pi. This is along axis, and field perpendicular to the axis. You are taking a point. You are taking a point, and the point lies on a perpendicular to the axis of the dipole. This is the axis of the dipole, the line joining the 2-point charges, and your point lies here, to the axis, perpendicular to the, your point is lying at a point on the perpendicular to the axis. And what about in magnetism? In magnetism, you write, this is your north. Say this is your south pole, this is your north pole, this is the axis, and your point lies at a point on a perpendicular to the axis. And in this case, field perpendicular to the axis. Then you have here a formula E equal to electric field minus 4 pi epsilon naught p by r cube. The meaning of this negative sign will be the direction of E is opposite to the direction of this one. And here, see, in a similar way, here also we have B equal to mu naught by 4 pi m by. So these formula are not required. I just wrote similarity. These are not required. In previous, in very older syllabus, we had these things, but it has been removed. But still, you can just go through this one. So now we can finish one more topic, a small topic today. And after finishing that topic, we will be left with only one topic of this chapter. So in next class, this first chapter will be over. After finishing dipole moment of an revolving electron, we'll be left with the galvanometer and its conversion to ammeter and voltmeter. That will be the last topic of moving charge and magnetism. So let's save this one and let's clear this too. So next we have to calculate magnetic dipole moment of revolving electron. We can follow Bohr's model, Bohr model. We can assume, assume that our electron is moving along a circular orbit. So we can say this is your nucleus. If the atomic number is Z, how much will be the charge on the nucleus? If the atomic number is Z, if the atomic number of given atom is Z, then how much charge will be there in the nucleus? If atomic number is Z, this means you have number of protons equal to Z, no? Because atomic number represents a number of protons. So if the atomic number is Z, then you have Z protons, and the charge on each proton is E. So the nuclear charge will be Z. Neutrons are chargeless. The charge of a nucleus is only because of the protons. Now say our electron is moving in an orbit, this one, and it has some radius. It has some radius r. And our electron is moving in this direction. Let its velocity be v. With v velocity it is moving, our electron. Now we can calculate the current in the loop. The current in the, you can say, loop, or yes, this is a circular loop. Our orbit is circular loop. Why? Because the charge is moving. The charge is moving in this circular path, and because of the moving charge, you will have current. So this orbit can be considered as current carrying loop. Current carrying in a loop, because electron is moving along the orbit. So how much is the current? How much is the current? You can calculate. We know the time period. Let's take the charge in a Q is moving. So the charge is Q, and let's say time equal to time period. Capital T is the time period. Charged by time interval. If I ask you what type of current is this, instantaneous or average current? What type of current is this, instantaneous or average? We are dividing charge by time interval. This time interval is equal to the time period of the electron. So when you calculate the current in a given time interval, the current is average. So actually this one is average current. And what will be the value of the time period? We can write, and in one time period, so the electron will cover a distance equal to 2 pi r, and time is equal to what? Path length or distance covered by a speed. No. So your your time period is 2 pi r by v. So we can just put the formula. Q is E here. Time period is 2 pi r by v. So your current here is EV by 2 pi r. The current in the orbit, this is EV by 2 pi r. You may also get a MCQ based on this formula in current electricity. Now you know the current, you have the radius, so you can find the area of this loop, how much will be the area of this loop, pi r square, pi r square will be the area of this loop. So how much is the magnetic moment? The magnetic moment. What will be the formula for magnetic moment here? For electron, we are representing a magnetic momentum by mu. By mu, we are representing the magnetic moment by mu for a. Now tell me, how much will be the formula? You know the current, you know the area. How much will be this? Current times area, you already studied. You have only one loop here. So want it to be current into area. You have the value for current V by 2 pi r, and you know the value for area pi r square. How much is left? This 1 r cancelled out, pi and it cancelled out. Then how much will be left here? You have pi is also, you have E V 1 r by how much? E V r by E V by 2 pi r. Okay. E V r by 2 is left. Pi is also cancelled, no? Yeah. Pi is also cancelled. So this is the formula for your magnetic moment of the electron, EPR by 2. Okay. Is it clear up to now? If you have any doubt, let me know. I think I saved this one. So let's have some space. Okay. Let's have some space. Let's clear the upper part. I am also removing this diagram. I have already set. Now, according to Bohr's model, up to class 12, we follow Bohr's model. According to Bohr's model, the angular momentum of an electron is quantized. It's expressed as L equal to mass of electron, speed of electron, radius of the given orbit, and this angular momentum is nothing but the integral power of h by 2 pi. Means if your electron is in first orbit, you put the value of n as 1. So it is this n actually represents principal quantum number, the orbit in which your electron is located. So if it is in the first orbit, you put the value of n as 1. If it is in the second orbit, you can put the value as 2. And so n is integer here. 1, 2, 3, dot, dot. It is actually principal quantum, quantum number. You might have any studied in chemistry. Okay. So this is the formula for angular momentum, mv, are equal to nh by 2 pi. Now, we have the magnetic moment of the electron, magnetic moment of the electron as EVR by 2. We can put the value of V VR from here, we can express VR as, we can express in a VR as L by VR as L by mass of electron. From this relation, you can write this was angular momentum by, and so you have E by 2, and VR is L by mass of electron. Mass of electron. So we can also express magnetic moment of electron as E L by 2m, E, where L equal to n, what is L? L, you can write it as also nh by 2 pi is angular momentum of electron. Angular momentum of electron. Okay. Or better will be write it as like this. Everything, So L equal to MVR equal to NH by 2 pi. I have already written here. So sometimes, if a speed is given, that S is given, then you can express, this L as MVR, you can just put the values in MVR here and find the values. If, if you know the principal quantum number, the value of L, then you can simply calculate L from NH by 2 pi. Where H is, what is H here? H is Planck's constant. H is Planck's constant. H is Planck's constant. And if you write this in vector form, in vector form, if you write this in vector form, then we can write, see, this is just the magnitude of magnetic moment of electron, magnetic moment of electron in a particular orbit. Now, if we write this in a vector form, then we'll put charge as minus minus E, because the charge of electron is minus E, and everything as such. And what will be the meaning of this minus? This minus will represent here, this minus indicate here, here that direction of magnetic moment of electron is opposite to the direction of opposite to the direction of angular momentum. Is it clear? Let's save this one. So we also finished this topic. Let's try a few questions, and in next class we'll study galvanometer and its conversion into ammeter and voltmeter. That will complete the very first chapter of this electrodynamics part, moving charge and magnetism. And after that, we'll study this magnetism and matter. That won't take much time. That is a smaller chapter and theoretical. Let's semi-clear this one. I will give you a question and we can try